Okay, the last presentation session of the Breakthrough Technology Conference, and this session focuses on iron-bearing raw materials, iron ore, scrap, and metallics. The equation is simple, isn't it? I mean, the higher the quality of our iron-bearing materials, the lower the emissions we should get out of our furnaces. So with increasing decarbonization pressures, we can look into the obvious decarbonization solution, increasing the average quality of our iron-bearing content. But unfortunately, it's not that easy. First of all, limited availability, especially for the higher quality segments, iron ore, scrap, all of these. These segments have typically been very tight, so it's not really easy to see significant increases in the overall supply overnight. These really require investments now so that we can start seeing an increase, a meaningful increase in the supply of these raw materials over the medium term. And there is our first concern, especially in the context of the R-grade material availability, if the investments that are being implemented now or in the near term, to be implemented in the near term, will be enough to meet the decarbonization plans of the steel industry. From availability, the second issue is beneficiation and upgrading. Now, many studies show beneficiation of iron ore, upgrading of scrap results in net emission savings. But then where to do the beneficiation or upgrading, at the mine site, at the recycling site, or at the steelmaking site? And who is going to pay? Who is going to pay for the cost of beneficiation or upgrading, and who is going to benefit from the results of upgrading and beneficiation? And lastly, from transportation to the storage, to sorting, cleaning, all of our processes around iron-bearing materials. What is the potential for improvement? And how can we tap that potential and enjoy higher efficiency, higher energy efficiency, and hopefully lower emissions? So this session is organized around these questions. And first, my dear friend, renowned EAF expert Jeremy Jones will join us. The title of his presentation is Optimization of EAF FE Feedstock as related to steelmaking and decarburization. Jeremy, please join me on stage while I make a very quick introduction. Jeremy is the president of Continuous Improvement Experts and a distinguished leader in the global steel industry. He specializes in process optimization across full spectrum of steelmaking technologies, with previous senior roles at major firms Tenova, Bechtel, Hatch. His experience spans projects in over 100 countries. Jeremy, thank you for joining us, and I leave the microphone to you.
Thank you for inviting me. Okay, is it? Yep. So just the usual disclaimers up front. So I'm presenting this on behalf of my own group, Continuous Improvement Experts. Also IIMA, I'm a technical consultant to IIMA, so I get involved in a lot of iron-making technologies and other things. So when we look at further decarburization in the EAF, it's very, very dependent on renewable energy, but also on higher quality raw materials. Because as you'll see, using lower quality raw materials creates greater energy inefficiencies. For greater amounts of renewable energy to be made available, we have a lot of work to do, because it's not just about putting in a solar field or a wind farm. We have to upgrade the distribution grid. We have to develop more efficient storage technologies and more efficient renewable energy technologies. And we've seen a lot of advances in things like solar. We have some panels now that are closing in on 50% efficiency. 3 years ago, the best we could hope for was around 20%. So there's a lot that has to be done. Hydrogen-based processes, I made this prediction 3 years ago at a conference that we wouldn't really see much before about 2035. I still say that, and I think mainstream, we're looking at more like 2045. So if you're going to implement those, you're really looking at Scandinavia and Canada, where they have a large amount of renewable energy already, where it's more likely that they can implement some of these things with hydrogen. So scrap is a decarburization lever. 100% scrap-based operations already have a very low carbon footprint. However, I need to qualify the fact that people say, well, when you recycle scrap, then the CO2 footprint associated with that scrap is zero. Well, that would be true if it was all iron. But because it contains impurities, those impurities create a carbon footprint in the scrap. And that's something we're going to talk about a little bit later. The footprint can be lowered through improvements in efficiency and iron yield. But we have to understand the properties of scrap to optimize its value and use. And increasing levels of scrap residuals are a major concern, because these residuals can't be removed right now from the steel, which means that mostly the best we can hope for is to dilute them. And that's why you can't talk about the future of steelmaking without realizing that it's about how do we maintain circularity, sustainability, and the right balance between ore-based metallics and scrap. The better job we do of upgrading the quality of scrap, the less our dependence on ore-based metallics. If we fail to take steps to improve scrap quality, then it means that we're accelerating the need for ore-based metallics. So it's impossible to talk about decarburization without talking about raw materials. The single biggest cost for an EAF steelmaker is the metallic charge. The future of EAF steelmaking, as I said, is about maintaining a sustainable balance between ore-based metallics and recycled scrap. So another thing which a lot of people have been asking about is a decoupling of iron making and steel making. And I would say that for me, the answer is obvious. You're going to have a certain portion of iron making is going to be decoupled, because it's quite likely that for a lot of EAF operations, they will be reliant on a source of merchant OBMs. And so that inherently says that you're going to produce these somewhere else at a large scale that makes it more cost competitive, and then those materials are going to be purchased by the steelmaker. If we want to maximize the recycle of steel scrap, we can only achieve that by improving the quality. And that's true of any recycled stream. If you want to maximize the use of a recycled stream, the easiest first step is to improve the quality of that stream, and that makes it much easier and much less costly to utilize in a process. So some of the issues that we're dealing with, I guess I should have made that slide a little bigger, because I have trouble reading it even from right here. But things like the dirt and the gangue content in scrap, that's something that we can solve that issue right now. Non-metallics content of scrap, we have methods to solve that issue. Lack of definition of scrap characteristics. So several years ago, we used to have an EAF experts committee within worldsteel. And what happened was we actually developed a matrix so that we could identify what the nomenclature was for scrap in different regions of the world to create better transparency. But when we tried to adopt a global scrap standard for the world, we got a lot of pushback from the scrap processors because they said we would reduce their profitability by creating better transparency. Things like value and use, the understanding of value and use, we have very good models now. But the things that we're still fighting are the scrap availability. Is the right scrap available in certain regions? And the rising residual levels in the scrap. So with respect to the scrap available in certain regions, we look at the developed world, and we all tend to export a lot of scrap because we have a surplus of scrap that's not the right scrap that we want for the types of steel that we're making, or we have a surplus of it. So that happens in Europe, 20 million tons per year. In the US, 15 to 18 million tons per year. Now, when I talk about ore-based metallics and steel scrap, I think there are a lot of double standards. Because when we talk about OBMs, the first thing anyone ever talks about is gangue content. When we talk about scrap, the first thing anyone talks about is copper content. And we don't seem to worry about the fact that we have dirt. I had some clients that were importing scrap, and when we put in a separation process, we found that they were getting 7% dirt. 7% dirt is the same thing as having 7% gangue in your DRI or your HBI. It's probably not something that you would find acceptable. So we need to be concerned about dirt, extraneous non-iron-bearing materials, scrap oxidation, all of these things, which are typical standards that are applied to ore-based metallics. Things like the residuals, copper, nickel, moly, tin, must be controlled to meet product specifications. And currently, the way that we do that is through dilution. So essentially, ore-based metallics serve as a source of what I call clean iron units for the steelmaker. And then the differences between things like DRI, HBI, and pig iron is that pig iron allows you to use more chemical energy in your furnace, which means you put in more energy per unit of time. So it increases your productivity. Extraneous materials like plastics, non-ferrous metals, wood, oil, grease, these are the greatest contributors to environmental issues in EAF steelmaking. So you think that we'd like to get rid of them. We don't really want those things going in the furnace. The furnace is not, EAF is not an incinerator. It's supposed to make steel. So dirt, you know, is one that really most people just don't seem very aware of. It increases your flux requirements, increases energy consumption, your yield losses, it decreases your productivity. 1% dirt, when you look at how much flux you need to offset that, because the dirt tends to be acid gangue, results in an additional 43 kilos of CO2 footprint per ton of steel. For most people, that should be reason enough to take dirt out of the scrap. So just to go into more detail, this is analysis that one of my colleagues did for one of our clients in the US. And you can see that taking the situation, the as is, and then working that through, improving the removal of dirt, and also hitting the end point, essentially not overblowing the steel, can quickly get you $14 a ton in increased profit per ton of steel. So if I'm a 3 million ton a year plant and I can make an extra $14 per ton, yeah, I think that's a pretty good number. So what can we do to upgrade scrap? Well, the scrap grades with the greatest amount of free copper are typically shredded, number 1 heavy and number 2 heavy. Extraneous materials can be associated with almost all scrap grades, but predominantly, again, shredded, number 1, and number 2 heavy. Dirt, again, is associated with all scrap grades, but predominantly shredded, number 1, number 2 heavy. This is a processing unit developed by a company in Germany. We ran a number of trials where most people don't process heavy melt scrap. We process the heavy melt scrap using this equipment, and I'll show you the results just in a second here. So again, this whole thing of how much OBMs do we need? If we can clean the scrap up and remove a lot of the free copper that's not actually in the steel itself, then our dependence on OBMs is reduced. It doesn't go away. In the future, we're all going to be using OBMs in an EAF. Okay? The other thing we're fighting is that prime scrap availability is shrinking. The quality of prime scrap will actually go down as well as blast furnaces get phased out, because blast furnaces are producing automotive steel at like an 03 copper. From an EAF, we produce it at like an 08 copper. So as we transition to more EAF-based production, then the copper content, even in the prime scrap, goes up a little. Okay? So these are all things that we have to be aware of. Because of the situation in the Ukraine, the availability of merchant pig iron was greatly compromised. So several steel groups in the US began upgrading their shredded scrap, typically taking it from 0.25 to 0.3 weight% copper down to about a 0.16. And this reduced their dependence on pig iron for that. Now, copper can be removed by repeated shredding and magnetic separation, and you can use a process called ballistic shredding that produces very, very small pieces. But when you separate it that way, you end up with a stream that's very high in copper content and a stream that's very low in copper content. So now you have to find a home for that. We prefer using technologies that use the mag separations, multiple stages, and actually online analyzers that analyze the copper level in the product. And that allows us to produce very, very clean streams. And it also creates a recycled stream that's very high in copper content that goes back to the copper producers. So we need a much better effort in separating the free copper from scrap. So there are a lot of efforts on this with respect to shredded, and there are a number of steps you can take inside the shredding plant to improve the quality of the shred that you generate and to get a better split of the free copper. Typically, if you aim for a density above about 80 pounds per cubic foot, you'll find that the copper content is much, much lower. Okay? And typically, when we go to the lower copper, one of the side benefits we found was that as we do a better job of separating the free copper, we also separate much more dirt. So we typically see about a 2% yield improvement in iron. So with respect to heavy melt scrap, we ran a number of trials. There's a company called ȚIFTÇI in Germany that I worked with. We reduced the copper content of the heavy melt scrap by 0.15 weight%. We reduced the nickel by 0.04, chrome by 0.06, lead by 0.03, phosphorus by 0.02. With all of the extraneous materials, the plastic, the wood, and other things that we separated, if we had put those into the EAF, they would have generated 200 kilograms per ton of that scrap of CO2 footprint. Now that's a huge number when you're talking about EAFs have a CO2 footprint of 300 kilos per ton. So the problem is that people treat scrap as a zero CO2 footprint, when in reality it can have quite a substantial CO2 footprint. Energy savings were also huge. Now, to give you an idea, the cost of processing that was a few dollars per ton, and the savings, even if we just applied the CO2 footprint reduction, would have paid for that 20 times over. The argument has always been, oh, to process scrap and generate higher quality, the cost is too high. Well, that's a fallacy. One of the latest trends we've seen is that for very high productivity shops, they do additional processing of the scrap at the site. So several of our clients have proceeded with this in Turkey, in Italy, Arvedi, others in the US, and they might do an additional mag separation. They might remove dirt and copper. And so that provides really, really huge savings. The payback at a couple of these plants was less than 3 months. And the improvement in the consistency and reproducibility of the operations was huge, just huge. Okay, I think I just covered that. So we need to drive towards cleaner raw material input to steel making. Steel scrap plays a critical role. Can we improve the value in use? Can we improve the quality? The answer is absolutely yes. Part of achieving that is also working with the end users of the steel. So automotive makers, if they make it easier to separate the steel from the copper in the components of the car, then that makes it easier to have a higher quality recycle stream. And this all sort of factors into circularity. So are we going to talk about circularity, or are we going to do it? Are we going to talk about sustainability, or are we going to do it? The upgrading costs are more than offset by the reduction in CO2 footprint, EAF efficiency improvements, and reduced environmental concerns. The equipment is already available. We need more involvement from the scrap processors and from manufacturers. We need to close the loop on the circle. We need to design for end of life to achieve cleaner recycle streams. And regardless of what anybody says, OBMs are here to stay. They will be a part of EAF steelmaking for the foreseeable future. And they are part of the enabler for us to recycle greater levels of scrap, even as the residual levels continue to climb. Okay, thank you.
Thank you, Jeremy. I'm turning to our audience. Are there any questions for Jeremy? And while waiting for a question, maybe I can...
Yeah, there was one there.
Okay, please, third row.
These lights are really...
Thank you for a nice presentation. You mentioned that 200 kg of CO2 per ton of saving due to processing of the scrap, or link with energy, or?
This is removing dirt, removing wood, removing plastics.
Okay. So this is saving the energy and also CO2 emission through dirt.
Yeah. So when you remove dirt, then you remove the need for additional flux, which has a high CO2 footprint, right? When you remove the wood and the plastic, you're removing the CO2 that's directly generated by using your EAF as an incinerator. And so those are direct CO2 savings. So,
Okay,
you know, and every scrap stream is going to be a little different. But, I mean, those are the numbers, and we actually collaborated with Rogesa, because they're actually looking at some of these technologies to upgrade scrap quality for their EAF shop in Germany.
Okay, thank you.
So Jeremy, please, first row.
Is there any categorization regarding the scrap quality established in the world market?
Is there any
Type of scrap, categorization of scrap. How do you decide which type of scrap do I want? Basically, if we process for making steel, so we need to know that what kind of quality, that what kind of copper, nickel is available in that, because that will affect our processing and energy load also.
Yeah, so what you have to do is you have to do some process analysis.
Suppose the automotive industry, it is having some kind of alloying element which is not required basically for making simple carbon steel. So for removing the impurities basically which is not required from the scrap for making finished steel. So is there any categorized scrap definition available in the market?
Sorry, I don't understand your question.
So type of scrap, can you categorize scrap or that this kind of scrap is for that category, that scraps from automotive industry is for this category, scrap from other industries which are having heavy alloying element will be for use for some
Heavy
kind of...
machinery and things like that typically
Yes.
become heavy melt, right? So the heavy melt typically has a lot of extraneous copper with it because it contains a lot of wire and other components, right? So there's an opportunity to remove that.
Is there any mechanism for distinguishing different type of scraps basically?
Distinguishing the different types of scrap? Well, every region has its own scrap standards. That's what I mentioned. At World Steel, we tried to generate a global standard.
Yeah.
But the scrap processors didn't like that idea because transparency for them means lower profitability.
No.
So they like things the way it is. But yeah, you have to, look, you have to, as a steel maker, you can't just buy scrap and just throw it in the furnace and say, I'm making steel. You actually have to do some work in order to optimize your plant, you know? So there are steps you can take to understand your scrap sourcing and the quality and the impact on your operation in the furnace. So,
Thank you.
The gentleman on the third row.
Hi, thank you very much for your presentation. Very interesting. Then, yes, I think many of the steel manufacturers have been thinking about how to improve scrap manufacturers' quality. Do you have any idea to motivate them to improve scrap quality?
well, typically the easiest way to motivate them is if you understand the value and use of the material and you analyze how much savings you're going to get in the steelmaking operation. You give some of that savings to your scrap supplier and you keep some of the savings for yourself. So that's the easiest way to motivate them is money. But we also see where there's pushback from the scrap processors. So in the US now, Nucor, SDI, CMC, they all vertically integrated. They have their own scrap operations. So it's easier for them to get what they want, right? In some countries, we're seeing people putting scrap processing at site because their suppliers won't do the work for them, so they do it themselves, and they still find out that it pays off, that it's profitable, and that they improve the EAF operation, they improve the quality of the steel, and they improve the productivity of steel production. So that should be a message to a lot of other people who think everything's fine, I don't need to worry about it. If you look at the lowest cost EAF producers in the world with the highest quality, they all have programs to improve scrap quality.
Okay, so in that sense, scrap as well, or decoupling of supply of scrap and purchase of scrap is not working. So only way is for manufacturer to vertically integrate.
Yeah, and also what we do in North America, all of the flat product producers have what are called buyback agreements. And I explained this to a number of the European groups that are now putting EAFs in. You heard a couple mention this morning that they have agreements now. We take all of the prime scrap back from the automotive company. If we supply steel to an automotive company, we have a contract to take back the prime scrap. And that allows us to have higher levels of scrap in the furnace and to balance with the OBMs. If more and more people produce with the EAF and there's a higher demand for prime scrap, then we'll probably see a greater need for OBMs as well, because the availability will be a concern. Yeah.
Okay, thank you very much.
No worries.
Thank you very much, Jeremy.
Okay, thank you.
I think Jeremy's presentation provided quite solid examples of the benefits of rather simple, currently available scrap cleaning, upgrading technologies, and taking into account that our industry will be using increasing amounts of obsolete scrap. If my mind doesn't fail me, from about 450 million tons today to about 900 million tons in 2050, by 2050. The importance of these methods and tools, the potential emission savings and efficiency gains these methods can provide is quite important. Okay, thanks again, Jeremy. Next, we are going to have Mr. Marco OMETTO from DANIELI Automation. So far today, in different presentations, we've heard the importance of digitalization, for example, the keyword digital twins, but we haven't had a presentation so far focusing only on digitalization and the use of, for example, AI-based tools. So this will be the first one. Marco, thank you so much for joining us. The floor is yours. Marco will focus on the use of digital technologies in scrap treatment processes. And just a very brief introduction. He's been with DANIELI Automation since 1984, starting from project management to executive vice presidency, including the DG and MET laboratory. He's participated in over 20 European-funded projects. He was elected to the board of directors of STEP, and he's the author of over 60 technical publications, also holds multiple patents. Thank you.
Honored to be here today. The contribution of digital technologies in scrap treatment processes for the purpose of reducing the ecological impact in steel manufacturing. Those was the previous title I gave to this presentation when I decided to submit the abstract to the worldsteel. But looking to what was saying by my previous colleague, Jeremiah, talking about the scrap scarcity and what there is around scrap, I think that this is a continuous presentation of Jeremiah itself, because we are thinking there are no way to understand how much important is becoming scrap today, how much important is becoming for to make steel, but to make steel for spatial steel, for high-level steel, and that's the reason why we need to be as much as possible organized to manage those critical resources. Today we will discuss how digitalization can significantly improve scrap treatment and reducing CO2 emissions in steelmaking. Steel, as everybody knows, is central to the modern society. So we cannot live today without steel. So we have to find out a way to become sustainable and in the same time to become usable within this within our environment. I'm used to say that paper, cement, and metal are responsible for an important amount of CO2 emissions. But if you look to the various level that we will see later on of contribution in CO2 emissions, even steel is a large, important contributor. The talk today is organized into 5 main sections. First, I will give an overview of the European decarbonization strategy. Next, we will briefly explore the cooperation landscape, which is accelerating innovation in this field within Europe. And then we will examine the scrap-to-steel processing, the role digitalization plays along the chain. We will conclude later on by looking at the impact of these technologies on CO2 emissions. Steel production accounts for roughly 7 to 9% of CO2 emissions. Everybody already before me confirmed this value. Basically, blast furnace, basic oxygen furnace routes emit roughly around 2 tons of CO2 per each tons of liquid steel. And electrical furnaces, which is most of the time full scrap driven, emit significantly less, about 0.4, 0.7 tons for each liquid steel. However, scrap quality variability can strongly affect melting energy and therefore CO2 emissions. We have always in mind that relations that all the time we are increasing the energy needed to melt, of course we are going to increase the CO2 emissions. So there is a direct relationship between the cost of transformation and CO2 emission itself. The better we understand scrap, the more efficiently we can melt it. That's the reason why to invest in digitalization in this area. That is precisely where data and digitalization make the difference. As most of you know, Europe has set an ambitious target, becoming climate neutral within 2050, and reducing emissions by 55% around not later than 2030. These targets are supported by mechanisms such as emission trading system, which is increasingly discourage carbon-intensive production and motivation to the change. To support this intensive innovation, the European funds R&D project and pilot project program through Horizon Europe, the Innovation Fund, and not lastly, RFHS project, which are vertical for the steelmaking industries. And all those programs are promoting digitalization, electrification, circularity, and material efficiency. This creates a welcoming ecosystem for developing new technology, for scrap quality improvement, and low carbon steelmaking. An example that was already treated by my colleagues Klaus Peters in previous presentation is the Pure Scrap project, which is funded initiative involving several partners from industry and from research. The goal of this project is to deploy digital tools to better characterize and classify scrap, enabling accurate prediction of material quality before charging the furnace. What does it mean? To know, it is better than don't know. So how I see my colleague Jeremiah that is doing like that with his head, because it's true. Without having a perfect knowledge of what we are loading inside our furnace, we will not predict what will come out. And if we don't put in practice a strategy to increase the level of the quality of the scrapping, during the process from scrap to steel today, we will not have tomorrow a better quality. The quality will become always worse than now. How to do that? By combining a sensor with an AI-based algorithm and building a robust data model, scrap lots are assessed more reliably. This supports more effective batching strategies, reduces energy consumption, and ensures more consistent steel quality. Moreover, pure scrap, which is this important project for us, aims to reduce both cost and CO2 emissions by increasing scrap usability and reducing process variability. But let's briefly look at the scrap to steel chain. First, scrap is collected from a wide variety of sources, often with not homogeneous composition and levels of cleanliness. Pre-treatment and sorting to remove contaminants and improve density is a common practice today. Then processes control engineers establish the scrap mix to be supplied to the melting phases based on the target value. And finally, scrap is melted into the electrical furnace to produce liquid steel. Each step is characterized by energy use and consequent CO2 emissions. But at the same time, each step can benefit from digital tools that improve quality, traceability, and efficiency. How digitalization enhances the entire value chain. Data acquisition and traceability allows process engineers to better understand material characteristics before melting. Advanced sorting improves quality and reduces unwanted impurities such as copper and tin. And I would like also to add one more thing that is also important, and following the Jeremiah example, which is the sterile, which is impacting a lot within most of the massive steel productions, not only in Europe, but worldwide. And predictive batching system help selecting the optimal scrap mix, minimizing the corrective action on liquid steel itself. So knowing which could become the analysis of our liquid steel, even in the primary metallurgy, is giving us a gun to distinguish the values that has to be alloyed or not. And this is also another one important aspect that we have to consider along the chain. Finally, real-time furnace controls, which is the most important moment from where we are going to decide if we did the right things before to melt. Finally, real-time furnace controls and process models optimize melting condition to reduce electricity and oxygen consumption. Summarizing these various contributions can give a significant reduction of CO2 emission. Someone asked me, how much? So I would like also to remember that in the past, during some of experiments we did, and right now those experiments are becoming reality, having the knowledge of the scrap loaded into the furnace and not having in the almost 100 heats gave us as a benefit the decreasing of the standard deviation of the kilowatt hour per ton from 26% to 6%. This is one result, and this can be proven also. Now, let's get deeper on some of this context. Scrap comes with a high level of composition variability. We already mentioned that. Today, sourcing relies mostly on supplier declaration and manual inspection, which is often approximate and inconsistent. So we have to rely to what we feel, not what we measure. And digitalization improved this through advanced database system, supply scoring, and tools for predicting the chemical composition or contamination risk of different feedstock. I would also to say that digitalization gives also today the opportunity to classify automatically the scrap incoming into the various steelmaking facilities by means of the computer vision and artificial intelligence, which is segregating automatically the various types of scrap by following the various rules, the European rules, the Japanese one, the USA one. It depends by the rules that has to be applied. But the classification is also another one very important gun. This increases confidence in purchasing selections and helps achieve more homogeneous input material. Scrap treatment includes shredding, separation, removal of contaminants, and density adjustment. The aim is to improve the purity and the mechanical, chemical repeatability of the input material. Digital tracking during treatment provides valuable information such as mass chemistry and other parameters that can be attached to each scrap lot, improving predictability downstream. It is always respected the paradigm to know it is better than don't know. Better sorting and cleaning reduce residuals such as copper, and one of the main causes of the quality issues in the electrical arc furnace steel. Higher scrap quality means better melting performance and lower impact emissions. Another one aspect that is underestimated is logistics. Scrap may be moved several times before reaching the furnace. Every movement increases the risk of losing track of origin, chemistry, and mass. And digital solutions such as RFID, QR platforms, and real-time inventory platforms guarantee data continuity. Data continuity is really important also later on to calculate scope 1, 2, and 3 if someone has to make a balance of sustainability. This allows more efficient material flow, reducing unnecessary handling and giving to the process engineer real knowledge of what is stored and where. And the result, even in this case, is fewer disruption in batching and melting. Now, let's talk about batching, where the scrap knowledge becomes value. The better we know the scrap composition, and the better we can build the recipe that feeds the furnace. Digitalized batching combines data from suppliers, treatment, and logistics to create an accurate blends that meet target chemistry with minimal adjustment. Even in this case, this reduces melting time, and energy demand, and the need for additional, such as carbon or lye. In poor words, this improves productivity and lower CO2 emission. At the end, inside the electrical arc furnace, digitalization is today rapidly transforming operation. The predictive models are used to track melting behavior and then dynamically adjust parameters such as electrical power, oxygen, injection, and carbon usage. It is not of today to know there are so many of those tools running. If we are talking about DANIELI Automation, some one of you already knows the use of melt model, which is based on this concept. This ensures optimal energy uses and improvement slag forming, leading to the better heat transfer. Slag forming, of course, is part of one of the most important critical portion of the process of transformation inside the electrical furnace. Having the perfect composition of the charging, the models can also predict much more better the forming of the slag forming. Real-time data acquisition analytics help operators anticipating critical events, stabilize the process, and reduce the tap-to-tap time. The outcome is lower energy intensity and reduced CO2 emission, always the same. At the end, if we are going to look to the overall impact, when digitalization improves scrap value, enhances batching, increasing electrical arc furnace efficiency, reducing both energy and carbon consumption. And by reducing scrap impurities, process become more stable, energy drops, and consequently CO2. I would like also to add that it is measurable that this kind of practice is going to increase most of the time also yield. And combining all the improvements, digitalization represents a powerful and cost-effective lever to decarbonize EAF steelmaking. Now, let's put the focus on the conclusion. As it was mentioned several times in several different presentations, scrap is fundamental in achieving low-carbon steelmaking. We already see that even if we start from rough information today, we are emitting between 0.4, 0.7, which is 50% or more than 50% less than with the use of blast oxygen furnace. Digitalization is a key enabler for decarbonized steel production. Without the digitalization, it's not possible to measure, it's not possible to calculate, it's not possible to predict, it's not possible to add in ratio with what the process needs. And European practices accelerate this innovation through programs targeting digitalization and low-carbon technologies. By integrating data and models across the value chain, the industry can achieve measurable emissions reduction and support the broader, I would say, worldwide climate objection. Thank you, I finished.
Thank you so much, Marco. The digitalization from scrap to steel, so the whole process gate to gate, really. So any questions for Marco? Yes, Klaus, please.
Yeah, thank you, Marco. I could have also asked my question to the previous speaker, so please don't hesitate to maybe to compliment. I fully agree, of course, that measuring and get data on the scrap helps to have more promising processes within the steel producers. And I'd like to have your insights. How do you judge the existing and available technologies, both in regard to the measurement devices as well as the digital tools? Do you see they are available and it's just a question to apply them? Is there a need to do some additional research to become better? And if so, please give us some homework to do.
I mean, there are many technologies today which are approved. Most of them are based on computer vision and artificial intelligence to understand and to classify the material before income to the scrapyard or before income to the furnace itself. Those type of technology is giving just only one characteristic, which is the which is the geometry of the scrap which is incoming inside. It's not giving any information regarding the quality and the composition. This is another one, I would say, research and development area where to work. That's one of the reasons also we decided to participate to Pure Scrap project, which is combining together different kind of sensor. Some of them are already giving the composition of the material and combining this information with the one incoming from the computer vision and artificial intelligence and classification, we will, I guess, have enough to be as much as fast possible to analyze all the material incoming. One of the biggest barriers there are is the speed. The speed to analyze today by means of spectrography or LAPS or some others, not conventional sensor are very, very low. And this is, of course, a barrier because the quantity of material incoming into the scrapyard in a modern steel making, it's huge, and this is one of the things that has to be overcome. I don't know if I answered your question.
Sorry. Any other questions? Yes, please.
Thank you very much for your presentation. My question is, how do you think about the use scrap? In the scrap maybe have some radioactive material. So you use AI technology or you use digital technology, how to predict the radioactive material inside?
I mean,
thank you.
Both of them are necessary, if you don't have any digital solution to trace the material, you don't have any chance to build the models based on AI to predict the composition or to predict whatever you want to predict. We have to start from there. That's one of the reasons why, as DANIELI Automation, we invested on the platform before to start the investigation. Now, the way to collect those information can be several, but always based on digital solutions.
Okay. Marco, thank you so much. Next, we'll focus on Australian iron ore. Australia really lies at the heart of our supply chains. It provides about 60–65% of global iron ore exports. Hence, it's very important that we can use Australian iron ore in lower carbon technologies that we are considering. So we'll have Dr. Gesa from Hatch joining us to speak on processing Australian iron ore in electric steelmaking furnaces. He is a process metallurgy specialist with 14 years of global experience in engineering and research. His work centers on decarbonization in the iron and steel sector, specifically as a lead developer of Hatch's electric smelting furnace technology. He holds a doctoral degree from McGill University and serves as an adjunct professor at the University of Toronto. Dr. Gesa, please.
Thank you very much for the kind introduction, and thank you to worldsteel for allowing me to present today to talk about, again, the processing of Pilbara iron ore in the electric smelting furnace process, which has been covered by quite a few previous talks today, yesterday, and in the past couple of years. So again, we're focusing sort of a case study-based analysis for the use of Western Australian Pilbara iron ore, specifically to highlight the advantages in this process route. So a very quick introduction to those who are not familiar with Hatch. Again, we're a global multidisciplinary engineering, consulting, technology, and advisory firm based in Toronto, about 10,000 strong, again, all over the world, with a very strong focus on mining and metals industry, but also energy and infrastructure. Again, our major focus, if you're especially in the electric smelting furnace world, is in delivering, designing, and the technology package for electric smelting furnace for the ferrous, non-ferrous, and ferroalloy businesses and advising, of course, everyone from producers, financiers, bankers, investors, and government agencies. So a very quick overview about Pilbara iron ore. Again, we've seen quite a lot of breakdown in different iron ore supplies, grades in the past day or two. But this is a slightly different breakdown. This is by region was supplied. Again, as we can see, about half of the world's export or merchant iron ore is Australian. That's almost 900 million tons a year. And within that, that's probably 500 to 600 million tons of iron units. I think I added 3 tagline words to explain Pilbara iron ore. It's critical, efficient, and challenging. So again, just from the amount that's being used today in the world, I think it's fair to say it's a critical piece of material input for our global iron ore industry, iron and steel industry. That's pretty much a quarter of the world's iron units every year coming from Australia. The majority of it comes from the Pilbara region in Western Australia. I think there's also a common misconception that we always think about Pilbara iron ore as a low-grade material. But I think the reason why it's considered low-grade, but it's actually the blessing because Pilbara iron ore naturally exists in very high quality and iron grade. So it does not require any beneficiation. It can be used directly in iron making. So it's actually one of the highest grade of iron ore available naturally. So that's why it's used directly in blast furnace iron making, or we call DSO, direct shipping ore. And that is perhaps the strongest advantage in that because you do not need to grind down beneficiates, grind down significantly for beneficiation, is actually a very efficient use of our naturally occurring iron ore resources. Of course, there's also quite a few challenges. I think a couple of them are highlighted. I think slightly higher phosphorus content compared to some of the other iron ores available. There's a higher gangue content because we do not beneficiate it traditionally, not heavily anyways. And of course, particularly higher alumina content compared to some of the other iron ores. And because of the higher LOI, particularly from the crystalline water, it's still more challenging to pelletize, particularly in very high proportions, and it's limited use in DRI production and pelletized production today. But certainly blending it is one of the such solutions to allow it to be pelletized efficiently. But I think the tagline, the key message here is Pilbara iron ore, Australian iron ore, is an irreplaceable source of iron unit for our world, even considering the significant growth in scrap supply in the coming decades. I think we'll have to rely, whether it's EAF or new ways of BOF-based steelmaking, to rely on reliable, large, critical supplies and abundant supply of iron ore, particularly from Australia. So again, I think we're seeing quite a few different versions of highlighting the challenges of transforming our iron and steel industry. We have traditional blast furnace BF-BOF-based flow sheet up top, again, using the abundant BF grade or lower grade iron ore and traditional available coal and coke fossil fuels to make high quality steel and BOF. But you have at the bottom, which is DR grade iron ore, high quality iron ore, natural gas or hydrogen-based reduction, electric steel making process. I think it's sort of a trilemma, if you will. You can really balance low emission, abundantly available raw material, and of course the capital cost of trying to transform one way to the other. Because especially if you consider, I think a lot of the green steel transition we talk about these days, BF, BOF, complete overhaul into a DRI, EAF-based process, but also keep in mind the massive capex needed to transform your iron ore supply side as well. I would say, relatively speaking, converting BOF to EAF and BF to DRI is probably more tolerable than comparing, let's say, upgrading 900 million tons of iron ore from Pilbara every year from DR grade, BF grade into DR grade. And again, I think one of the previous presentations, Vincent mentioned the use of DR grade iron ore, the fact that we call it DR grade iron ore, is not really driven by the DR process, it's driven by the EAF process. The presence of that gangue really is the fundamental driver to why we need to beneficiate and reduce the amount of gangue that's carried through to the steelmaking process. I think this also highlights a little bit a concern of our definition of green steel. So what is green steel? To us, I think it's about making steelmaking sustainable in general, but I think there's more than one pillar to that, right? Climate sustainability and emission reduction, CO2 reduction is of course critical and most urgent thing facing our industry. But we can't forget, of course, economic sustainability as a business. At the end of the day, as an industry, you need to be cost competitive to make sure our society can survive on iron and steel products sustainably and run a profitable business in the process. And of course, sometimes quite often overlooked is the environmental sustainability aspect of it, which again, it's the non-climate related environmental factor, things like water use, land use, waste generation, natural resource depletion. So a lot of these aspects are not really prioritized these days in the sustainable steelmaking conversation. So that's why I want to highlight it's actually emission reduction is important. Costs, both OPEX and CAPEX, is important to the financial sustainability of iron and steel industry, and also raw materials. The sustainable and responsible use of our natural resources, as well as all the waste generation, land use aspect of it, is just as important than climate change for sustainable steelmaking. So with that, again, I think this topic has been discussed extensively about the impact of high gang and I guess the beneficiation driver for using DR-grade iron ore in EAF. This graph will try to illustrate that. So the 100% baseline is, let's say we have a hypothetical 67% Pilbara iron ore heavily upgraded and beneficiated into a pellet and to be used in the DRI-EAF process. If we decide not to beneficiate as much into a roughly 64% iron ore pellet, or not beneficiate at all, 61% or 64% pellet from 61% pellet feed, that's the rough impact on the EAF operation from an efficiency and yield perspective. I think as Jeremy's presentation talked about earlier, it's primarily driven by that gang and the probably multiple times higher gang slag generation, fluxing needs, and associated iron yield losses that drives the performance impact to EAF steelmaking that makes it the beneficiation and removal of gang from the DRI, from the pellets, so critical for EAF steelmaking. So I think it's, again, without belaboring the point again, what the key is then, where is the best place, or how do you most effectively and efficiently remove gang material from this DSO run-of-mine that's available in Australia from Pilbara iron ore. So the two most common strategy we use today is either intensive wet beneficiation, which is physical removal, comminution, followed by some usually wet beneficiation to remove the concentrate, and because you're grinding it down so much, often requires agglomeration afterwards. Again, the most traditional way of upgrading lower grade iron ore into DR grade. And of course, what we're proposing today, and broadly speaking, is pyrometallurgical processing for gang rejection using electric smelting furnaces. So instead of physics-based separation, where it's flotation or magnetic, is the use of energy to melt and the natural phase separation of metal versus slag. And then the benefit, of course, you produce a higher quality, fully gang-rejected molten metallic product, but of course, it is more energy intensive because you are melting something at 1600, 1500 degrees. So really is the question of which one makes the most sense, in particular for, in this case of my talk, Pilbara iron ore. So a little quick detour about electric smelting furnace, electric iron making history. It's not a new process. It's been around almost as old as electricity itself, from the early electric furnaces in the 1900s. And iron making ESF started probably in the 1930, to Slunhold iron making ESF. And throughout the history of Hatch, for almost 70 years, we've been designing, supplying, building, and helping our clients delivering these kind of furnaces for the ferroalloy, iron making, non-ferrous, and PGM metals furnaces. Again, I've highlighted in red most of the furnaces that Hatch is involved in. Again, it's a very consistent and reliable technology that's available for many decades. And I always find it interesting that this question, will electric iron making furnace replace blast furnace, has been around since the 60s. So that plant was rotary kiln DRI feeding and ESF to make hot metal for BOF steelmaking. And that's from 1963. So it's definitely not a new technology. It's been reliably operating commercially, albeit for very different iron ore and different drivers for many, many decades. So a little closer look at what this technology looked like. Of course, Hatch is one of the suppliers of the ESF technology. In our iteration, we call the Crisp Plus furnace. In this particular application, it's about integrating with the DRI process so that you can effectively melt and separate the gangue from the metal in the DRI, at the same time having energy integration to improve energy efficiency, as well as yield improvement from effective gangue separation and the possibility to reuse a lot of reverts, both upstream and downstream, to maximize your yield and recovery. And at the same time, in the electric smelting process, it's essentially electrifying the bottom half of a blast furnace where you have final reduction, separation, and all of these nice chemical reaction, high temperature, by using electrical energy as opposed to fossil fuel to really drive the decarbonization effort. So some feature of the furnace is, again, we say ESF and EAF are just one letter difference, but the furnace looks completely different, operates more like a blast furnace and not a EAF. It's a stationary large furnace with 6 Soderberg electrodes. The roof doesn't open, in fact, it's very well sealed. It runs very strong reducing atmosphere, and with a very robust crucible that lasts a very long campaign life comparable to a blast furnace. In fact, one of our electric furnaces, the longest campaign life today is we're approaching almost 50 years, so a single campaign for the electric smelting furnace hearth. So they do last a long time, unlike EAFs. So today, my talk is mostly based on a scenarioed process analysis, starting from the run of mine in the mine, essentially, going all the way through, in this case, to iron making. So it's a result of quite a while of intensive work with a few clients, looking at all aspects of this flow sheet, whether and analyzing all the possible permutations of this flow sheet, whether do you beneficiate, how much do you beneficiate natural gas or hydrogen or a mix of both as reduction, do you agglomerate or not, shaft versus fluidized bed reactors, the choice of chemistry and slag engineering in the ESF and versus EAF and BOF steelmaking. So it's we've done a very extensive modeling with first principled process models, starting again from the run of mine all the way through your iron and steel products. And we've analyzed so many different things, but for the talk today, we really want to highlight the key question, which is what is the best decision or best path forward for Pilbara iron ore, which will zero in on the degree of beneficiation is a particular question, and focusing on those three key metrics, what I mentioned earlier, which is, again, what I think is the 3 pillars of sustainable steelmaking. Is it cost effective? Does it achieve effective decarbonization emission reduction? And does it have a responsible use of our natural resources from the environmental perspective, both in waste generation and resource depletion? Again, and of course, OPEX and CAPEX analysis associated with it. So we'll go over some key findings as well. Next slide, which I think this is I'll say the tagline result, right? Comparing whether in the top, which is you have DSO run of mine from the Pilbara iron ore, going through pelletizing, shaft furnace reduction, and then going to ESF or gangue rejection, producing roughly a ton of hot metal, versus the middle, which is doing BF grade beneficiation, and the bottom, of course, beneficiating intensely all the way to DR grade, and then in which case the product is about a ton of DRI. So 1 ton of equivalent ore-based metallics. I think the biggest difference you see there is the total iron yield comparing to from where you start, which is a run of mine. The yield difference is quite significant. Roughly 2% increase in the iron in the pellet is about 14% yield loss across the entire value chain, starting with the run of mine. So getting to approximate commercial DR-grade iron ore is almost 30% iron yield loss compared to unbeneficiated DSO-grade Pilbara iron ore. So I think that we can be quite confident saying that not beneficiating at all is probably the best options. Again, you try to avoid beneficiation at all if you really want to preserve the best advantage of DSO iron ore, which is in efficiency, be able to use it. And the ESF is very effective at handling the high amount of gangue that's coming in, rejecting as a slag, not only as a slag with a low iron yield, but also as a reusable resource for the cement industry. I think that really highlights both the economic as well as environmental sustainability aspect of this process. And of course, on the bottom, you basically, instead of 1.6 tons of iron ore per ton of OBM, you basically need about 2.2. And yield difference is not just an economic factor, but any yield loss is going to turn into either a solid waste, steelmaking slag, or something like that, or a tailing in beneficiation. So it covers, it's a impact that stretches both across the cost, economic, as well as environmental waste generation aspect. So I think it's something worth highlighting. I think when I first did this analysis, I think it's also quite surprised to find out how much of an impact on overall iron use when we start accounting the iron units from the moment it leaves the ground. So the second thing is we look at, so we know the ESF is very effective at removing gangue, but the question is still, for a pyrometallurgical electrified process, is it really energy efficient in a way and of course from the energy and emission perspective, is it the best way and most efficient way of rejecting that gangue versus beneficiation? So what we did is unbeneficiated, moderately beneficiated, and heavily beneficiated Pilbara iron ore in the ESF process. What is its impact from emission comparing to, let's say, I won't say typical, but a very well-performing BF producing pig iron. So I think, and we broke down the emission by different scopes, and from the iron maker's perspective, of course. I think the few key findings, I think the scope 1 emission, which is quite comparable, which is essentially your natural gas and so on. The scope 2, which is energy requirement, the electricity for the furnace, of course, the more you beneficiate, there's less slag, less gangue, so the emission does go down, but not by too much. And of course, scope 3, again, that's mostly from the pelletizing of the additional ore and so on. So there's also a decrease. The more you beneficiate, the less you have to pelletize, the less you have to melt. So there's a slight decrease in emission from beneficiating before going to ESF. But I think one of the things this doesn't account for is that mining operation is relatively small emission footprint compared to iron making. So all the investment and OPEX and CAPEX we invest in the mining and beneficiation operation doesn't get captured very well if you do a simple ton for ton emission calculation. And the second thing is, whereas you see the scope 2 emission drives a lot of it, we do see in the future with the greening of the electrical grid, this gap of how much emission difference can you derive from beneficiating or not beneficiating, or the gap to close even more in the future. So I guess the general conclusion is beneficiating Pilbara iron ore does help reduce emission, but not by too much, and that gap is expected to shrink in the years to come. And then we look at the same scenario, but from the cost analysis perspective. So I think the minor energy saving emission also translates to the savings in energy cost, but what really drives it is the very, very heavily increasing cost in raw materials. And this is just the money you pay to get the amount of run of mine, and doesn't even include the levelized capex for the beneficiation activities and so on. So I guess what we can see is that the emission benefits is rather small from beneficiating all the iron ore for the ESF process is very much overshadowed by the increase in operating cost. And of course, and associated yield differences. So again, just summarizing all of these things together, when we compare again, the 100% baseline is for unbeneficiated Pilbara pellet DRI ESF process versus beneficiating moderately to a BF grade, and of course heavily beneficiating to DR grade. I think the key message is, number one, the increase in operating costs is overshadows and outsizes the emission reduction gain from that beneficiation process. So is it, do you want to spend additional 11% OPEX to reduce the emission by, let's say, 5%? So that's a trade-off I think people need to make consciously. And of course, overall yield loss is the big driver. Again, like I said, if you look at the last two, slag rate in the ESF is a lot higher when you use unbeneficiated ore, which contributes to much better yield performance, but also contributes significantly lower iron ore consumption, which means reduction in tailings generation. Again, whatever gangue that's dug out of the ground, if it does not end up in the so-called good slag, which is iron-making slag that can be reused in the cement industry, will either end up in the tailings dam somewhere or into a steel-making slag dump or waste in low-value applications, such as aggregates, for example. So again, really the key message is if you have the ability to not beneficiate at all, I think that's probably the best. And if you do beneficiate, Pilbara iron ore's nature and generally speaking, upgrading to BF and DR grade iron ore, unless you have a very amenable ore that's very amenable to low cost, efficient beneficiation, smelting is probably the much better way to deal with that particular iron ore in the process, especially look at the entire value chain from the mine and mining perspective. So going off a quick conclusion, I think the ESF technology is a uniquely suited technology to process Pilbara iron ore, especially the DSO grade. It unlocks it as an abundant, efficient, and cost-competitive raw material for low-emission steelmaking, which is irreplaceable source of iron for the industry and for our world. And the DRI ESF process allows Pilbara iron ore to retain its biggest advantage, which is having no need to be beneficiated at all. While you have emission and energy costs to melt that gangue in the ESF, but it pales in comparison to the total cost, yield benefits, and at any level of beneficiation, really. And the ESF process we haven't covered in this particular analysis, but we've done a lot of case studies on that as well, is fully adaptable to all kinds of DRI fuel, whether it's hydrogen or natural gas or a mix, different processes, the reuse of up and downstream reverse, the addition of scrap and so on. Is a very flexible process. And I think some of the other technical factors are not presented today, including the chemistry of that gangue. For example, I mentioned earlier, Pilbara iron ore have a slightly higher alumina content, but that's actually advantageous when using the ESF process because it produces a higher alumina ESF slag, which cement makers actually prefer, and you don't have as much need to dilute it down compared to, let's say, blast furnace having trouble getting above, say, 15% alumina in their slag. And of course, higher phosphorus, having a hot metal-based metallurgical process allows very effective phosphorus removal, whether it's hot metal pretreatment or BOF steelmaking. So it's again, it's a very well-suited process for all kinds of low-grade iron ore, but particularly a very effective solution for Pilbara iron ore in general. So thank you very much.
Thank you for your presentation, Dr. Gesa. Any questions on the use of ESF technology for Australian iron ore? Klaus, if I'm not wrong, please.
Yeah, thank you very much. So it's not specific, my question is not targeting the specific iron ore, but more general, as you presented yourself as an ESF expert. Maybe you can elaborate a little more on the electrodes. So there's a high symmetry in the ESF, but I'm interested to know whether all the electrodes are really identical, copy-paste, or whether there is a difference among these. And how do you see the future of the electrodes if the number of EIFs and also the ESFs is increasing? Is this easy, or are there other issues lying ahead of us which we have not talked about yet?
Yeah, I think a very good question. I think in general, the electrodes are, first of all, Soderberg electrodes, so electrode paste rather than graphite electrodes used in EAF, which we see one has a big advantage in OPEX and from sourcing electrode paste as opposed to a graphite electrode. And then I personally, from all the ESF we designed, I don't think we have, specialized design electrode 1, 2, 3, 4. So I think it'll be a uniform electrode design just from a standardization, optimization of design operation. It is better. It is the standard way of doing it. In terms of going forward, I didn't quite understand your question. Is it on the electrode supply side or? Again, Soderberg electrode is very widely used, and I would say the OPEX advantage of Soderberg electrode versus, let's say, graphite electrode for EAF is an advantage for the wider and quicker adoption of ESF as a dominant process route for lower grade iron ore.
Any other question? Yes, please, over there.
So you said that, between the comparison of 61% Fe versus 66, something like that, you said that 61% Fe doesn't need any beneficiation. It can directly go to ESF and still it is economical compared to the 66%, I mean to say compared to the beneficiation. So whether there is is a break-even point, I mean to say, so if you bring down the Fe further, so then have you checked that at what level it will be, there's a break-even point in terms of economics and, technical feasibility as well?
So thanks for that question. So I think we started with 61 in this case study because that's a natural Pilbara iron ore unbeneficiated DSO grade. But we did examine in case studies what we call sub-BF grade iron ore, let's say 58, for example, from all different sources. I think our finding is that ESF is very effective at gang rejection, even for even lower grade iron ore. While I can't tell you exact break-even point because it's subject to a lot of other factors, reduction use, grid emission factors, and so on. But I can say that if the situation is right, you can have a sustainable and economic operation at even lower iron ore grade in this process.
Yes, please, on the second row, if you could pass the microphone.
Thank you for this excellent presentation. A question regarding the ESF. The plant now in New Zealand, I think, is below 1 million ton per year. What do you see the future for the size of an ESF unit? Yeah. If, for example, for 2 or 3 million tons of hot metal production, is this one unit? Are there more units?
Yeah. So I would say from our perspective as a technology supplier, 120 megawatt is fully ready to go today, which that will, depending on the feed, that will give you roughly 1.5 million tons of hot metal per year per furnace. And considering all the various pieces of technology, for example, electrodes, tapping, refractory, all the pieces are probably ready to get you up to 160 megawatt fairly quickly. Maybe the second generation of our technology will probably get you to 160 megawatt. And I think the real question is pairing it with the right size DRI reactor, right? A large 2.5 million ton DRI reactor, probably 120 megawatt furnace would be a very good fit, and also incorporate additional ability to recycle reverts. A larger furnace, perhaps a 2-point-something million ton DRI plant, plus a 160 megawatt single furnace may make a good pairing as well. So I think scaling up is as much as a technology readiness issue, but also a plant configuration issue. But the technology maturity, I think, 120 megawatt today, 160 megawatt next generations, we're very confident it's a very mature technology.
Any other questions? If not, Dr. Gesa, I have one question. I thought it was challenging to pelletize Pilbara iron ore.
Yeah.
So here, are we coming over those challenges? Because I see it starting from 61%. I think typical Pilbara iron ore is meant there. It's pelletized, and then the ESF operations were investigated, and then the beneficiated iron ore. So can you please explain?
Yeah, so again, there's certainly been a lot of development in pelletizing and other agglomeration technology for Australian iron ore. Again, we've analyzed that as some of the many cases. For example, the non-pelletized, fully diced bed process also works with very similar outcome as pelletized shaft furnace-based process for this ore. And again, pelletizing issue from Pilbara ore is primarily due to its LOI. And I think with the right amount of blending with other ore, pelletizing is certainly possible. And I think that's an angle where the ore suppliers are actively working on. Okay.
Thank you. Thank you, Dr. Gesa.